I am Anita Wasilewska, Stony Brook University, and I'm professor here. And these are lecture notes for the course or two courses on Introduction to the Theory of Computation. That's why I put the title Introduction to the Theory of Computation, and they have numbers. But the course or course's textbook is Elements of Theory of Computation by Lewis and Papadimitriou. This is, I consider, the best book, but everybody has preferences. It's pretty an old book, but extremely solid, and this is a second edition of that book. Also, the book is very concise and beautifully written. So the lecture notes I present are extension in the sense of explanation of all details which authors might have skipped, thinking that everybody knows much more than it does. And I followed the book very closely. So I do the book chapter, I follow my lecture notes chapter by chapter. So here is chapter 1, which are sets, relations, and languages. And that chapter is designed to bring back your knowledge, if you already have it, or to give you the knowledge of all parts of discrete mathematics which are needed for the theory of computation. And so I follow a little bit that path because it's important to have everything together once you take the course. So I've divided the slides into sets. So set 1 are sets, relation, a special type of binary relations. Set 2 is finite and infinite set and fundamental proof techniques. This is quite an important part. And then you talk about this is closer connected with theory of computation, which talks about closures of relations and algorithms. And then we have alphabets and languages and finite representation of languages. So that part is really already the beginning of pure theory of computations. The previous parts are just establishing what we know and establishing also the proper notation. Like, for example, we write A in A. It means that A is element of A, and A, capital A, is for the set, and empty set, we denote this is important. This is empty set. And we write A is element of A, element. And so, for example, let's take the set, which is so this is a set, and these are finite sets. So we define the set by listing the elements and which are the elements of the set. So it's just you have one element, so which is the set which has A, letter A is the only element, is element of A. Now this is another element of set, which is a little bit more complicated, but what does it mean? That this element of this set is a set which has the set which has only number 1 as the only element, and of course you have that 1 is element of A, this number, and 2 is element of A, and you can see they're all different creatures. So this is example which shows you that, first of all, finite sets, we can list the elements, and that means that this is a set, so the sets can be element of other sets, and here this set is element of one set, and this set is element of the set A, so the things are a little bit more complicated. So this is another example. Also, the sets we define the sets in different ways. In between, we can, so that was definition of a set, which was by listing the elements, but we can often define the set by the set of all elements of a given set, which fulfill certain property. So, for example, let's be set of natural numbers such that n greater equals 3. So it's infinite set of all numbers. So this is a property. So some sets are given by properties, and especially finite or infinite sets. And now you have set inclusion. So I brought it that we use the inclusion is less equal. And so it's improper inclusion. And proper subset is just a subset of B. And now we have also another notation that once you have inclusion of sets, you have the set of all subsets of a given set. So this we will use two notation, P A, which is the sets of B, that B is a subset of A, is the same set, but there are two notations, and we use, the book uses mainly this notation. This is another notation of the set of all subsets of a given set. So I bring it, and then we define algebra of sets. You define union, intersection, you have, and of course, another OR is propositional connective, and we use the same notation for OR if you write it symbolically, because really there's a connection with union of the sets and OR, so we often use the same symbol. And you have complement, relative complement, you have all basic operation of sets, and algebra of sets consists of properties of set that are true for all sets involved, and we use tautologies of propositional logic to prove basic property of algebra of sets, because you can see the definitions are connected in a special way. Another important notation is, so we already defined the set of all subsets. We define operations on sets, union, intersection, and complement, and you have another operation. So first, F is family of sets. It means what is a family of sets is a set which elements are sets. So F elements, all elements are sets. So we say also collection of sets. And union is, you don't know how many. So if you have 3 sets, for example, you have here, you have 3 sets. Let's say you have, this is family of sets because this is a set, this is a set, this is a set. This is a very nice set. Just to remind you, this is an empty set, but this is a set which contains an empty set, which is non-empty set, because empty set is element of that set, which has only one element, which is empty set. So here you have 3 sets, 1, 2, 3, A1, A2, and that is a family. So union of this family would be the normal union, so would be A empty set B. And because, so when F is finite, is just normal union, but if F is infinite, you just write that this is the union of all sets which are in the family F. So that is the proper definition. And then the same you do for intersection. for f, if the f is a family, finite family, it's a normal intersection of sets, but you extend that definition to any infinite family of sets. And the next important notion in algebra of sets is Cartesian product. It means you start with ordered pair. So ordered pair is A, B, where A is in A and B is in B, and you define Cartesian product or cross product. A, B is the set of the pairs that, and these are called ordered pairs, A in A and B in B. So you have the Cartesian product. And then you have the whole algebra of sets. Now, we need a Cartesian product of two sets. If you have Cartesian product of two sets, we define a binary relation, and we say that binary relation defined in a set A is any binary relation is any subset of A times A. So it's a set of pairs, and you have a definition of domain and set of values of relation. And we generalize the definition of Cartesian product of two sets to n Cartesian product of n sets. So we introduce the notion of ordered tuple, and then you have an argument relation for the same way. And again, I'm not going to go through all these definitions, but it's good to know that there is a place where you have all the definitions. So that is one of the roles of the chapter 1. So when you are in chapter 2 or 5 or 6 or 7 and you don't remember a definition, you have there, you say, what is a function? What is a function? We have a function. Here's a definition of the function. So again, I'm just not going to talk too much about it, but I want to bring two things. First, that special functions are special relations. So relation, which is a set of from A to B, A is called the domain of relation, and B is called the codomain. And if it is a function, we write it that this function maps set A into B. And what does it mean? You have relation is a function. If for any element of A, there is exactly one B, that AB is in relation. So that's why you write RA equal B. Notation, which we'll use, which we write, if we talk about the functions, we know that a function, one argument function is A, B. So the function maps A into B. So you can write that here you have set A, you have set B, and the function f maps A into B if this function, binary relation, is a function. And in that notation, in that definition, if you write f maps A and B, A is always the full domain of the function. So A is always the domain of the function. And then you have the range, which is the set of values and so on. And then AB is just a graph of the function. Of course, when you have function from real numbers to real numbers, if a function goes from real numbers to real numbers, so it means that the graph is A, B in function such that A is f of A and fb is fa. So it means that's why the graph is a real graph, because you have R. R, and your A, B's are elements on the plane, and you have a graph looks like this. But in our A and B can be any sets, so you still have the notion of a graph. Even if you cannot graph it, you can graph them only if your functions are on the domain, which are subsets of real numbers. You can talk about the graph in the sense of normal sense. So this is a generalization of the notion of the graph. Another important notion is the notion of the function onto. So f is onto if for all b in B there is a and a. So it means function is onto if all elements of B arrows go somehow to all elements of B. So this is onto because all elements of B have arrows. So that is the notion of onto. And also you have function 1, 1, that different elements have the different values associated with them. And special functions, which we are going to use, are 1, 1 onto, which are like exact mapping between two sets. And they have another, you have surjection, bijection, and so on. We use very simple notation. 1, 1, you know what it is, onto. So 1, 1 onto is a function which for any element A, for any element B, there is element A mapped into it, and also the mapping is 1, 1. And then you have compositional function, notations, and so on. So this is everything is there. Inverse function, which is also important. What does it mean when inverse function exists? Identity function. And of course, the identity is EA equal A. And you have a connection between inverse and identity. The next important notion, which we use a little bit, but it's good to know, and your homeworks are on that, that is the notion of image of a function. Again, the simple idea is that if you have a set, let's say x and y, so now function is x, y, and you have certain subset of x. So A is a subset of x, and I want to see what this function f does to this subset. So you take what's happening, the function does only of the subset, and you write that this, you talk the image of the set, and this is set B in Y, that the beginning of arrows are in the set A. And also another notation is f image of A equal, or FA, capital A, B. So that is the image of A under the function. And also you have the inverse situation, that you have set B in Y, and you have the inverse image of B, where B are in Y. So that would be, for example, this is not here. See? So the inverse image of B would be where the set here, where the arrows started. So for example, here, if you have a set B is here, the inverse image would be that inverse image of B would be that set. That would be not, because the value was outside the B. So that is the image and inverse image. The next important notion is the notion of the sequence. Sequence, and we write sequence is AN, an in n, and is any function on the domain of natural numbers with the values of a. So this is called the sequence of elements of a. And we write f, for example, fn equal, and shorthand notation, fn, you write nth element would be the, and this is a formula for the sequence. And also, sometimes we start sequences not from 0, because natural numbers, again, I want to remind that natural numbers is the set 0, 1, 2, 3. 0 is a natural number, very important number, natural number. So you can enumerate from 0, but often you enumerate from 1. So it can be just a subset of natural numbers, not the whole natural numbers. So that's what I said. And finite sequence, which is also a notion which I'm going to use, finite sequence is a function from finite set from 1 to n, when n is natural numbers, into the set A. So this is finite sequence of elements of A, and this n is the length of the sequence. N is natural numbers, 0 is natural number. So what happens when n is 0? Function is an empty set, because this set does not. This set is an empty set. Empty set cross product with any set is an empty set, so the function is empty set, and we denote. So we have the notion of empty sequence, and that's what we. E is empty sequence. And we use that notation. That some books use lambda. There are different notation for empty sequence. We will use E as a notation of an empty sequence, important sequence, which we'll be talking a lot about empty sequences. And there are some examples and examples. And you have examples of family. We have family of sets. You can talk of sequence of sets. What would be sequence of set? Is a function from natural numbers to the any family of sets. And also, and then you have generalized union. Because if you have a family of sets, instead of writing union F, you can write union n in n, a n. So these are all elements which are, there is S that, there is n that exists in some a n. And sometimes you write generalized union, because instead of writing a n in n, you can also write n equals 0 to infinity. So this is, or you can write union n greater equal 5 n in n. So that would be n equal 5 to infinity a n. So you have a generalized union of sequences of sets, and the same for intersection. Again, you can generalize it to any family of sets, that T can be any set. So you can have a family of sets which are indexed by, for example, real numbers, or even subsets of real numbers. So now the course, the lecture notes, the website for the course contains, that is addition to the book, a lot of simple short questions and long questions, which in the lecture notes you have basically almost all homeworks from the book, nicely solved and written, because I believe that you start to understand better if you have a lot of good examples. So also I should have said at the beginning that the video slides come with the full set of chapter slides. So on the course website, there is there are lecture notes, which are one side, but also they are specially made slides. If you listen to the video, you can have all slides which I am using for the video are available on the course website. So I created a lot of simple questions, which are pretty simple. So for example, I'll do one, just to, let's see. This is nice, right? The question is it true or false that 2 to the power 1, 2 intersection with 1, 2 is non-empty set? Intersection, this is a set, this is a set. Is there element in this? I can give you a second to think, but let's see how to approach it. That is a question. What does this mean? This is the set of all subsets of the set 1, 2. So it contains empty set, it contains one element sets, and it contains the whole set, right? So you can, if you are now, and this is 1, 2. So the question is this set, is this intersect with 1, 2? Is this set intersection of this with this non-empty? The answer is no, because it's an empty. 1 is not element of 2 to the power 1, 2. You don't have the set of 1, but 1 isn't, and 2 isn't element. Of course, you can see immediately that is impossible, because elements of this set are always sets, and 1 is just a number. So the answer is no. So they are, and so they are nice little questions. And of course, and there are more questions. And then, of course, there are solutions. So when you have slides, you can always check if you did it properly, if you solve your question properly. So there is a lot of simple questions and answers to those simple questions. See, more and more, 10, I think. So the whole structure of the course is that we introduce certain notions, and they will be more and more complex, and then I give you simple questions about those notions. So in this way, you try to not only remember the definitions, but also you understand what the symbolism and what those notions mean. So and then, so that is about the questions. Next part is special types of binary relation. Really, we have two considered for that subject, and basically they are the most important binary relations in mathematics. So it's equivalence relation and order relation. So first, I just want to remind you, you know what is equivalence relation notation. Important is always important notation. Equivalence relation, there are different notations. Notation. I think we will use this one more often. So we will use that symbol to denote equivalence relation. And what is equivalence relation is see, reflexive, symmetric, and transitive. So any relation which is reflexive, symmetric, and transitive is called equivalence relation, and we use different symbols for that. And equivalence relations are important because they have a notion. With equivalence relation, you create what is called equivalence class. So equivalence class is the set, is binary relation of B in A, that A is equivalent of B, and this is notation, and A is called a representative of that relation. And you have a notion of partition of a set. So equivalence relations, we have also connected with the notion of partition. Partition of the set, you've seen it. So you have A1, A2, A3, A4, and this is my set A. So it's partition into some subsets. It means they are disjoint, non-empty, and they end up to the whole set A. That's why it's called partition, and this is nice general definition. And once we have a set, we create, which is called quotient set. It means this is a set of all equivalence classes for A in A. So this is quotient set. And we have, and we prove, very nice theorem, that first, if you have equivalence relation, that set of all equivalence classes form a partition, and you have the full set. So if A is equivalence relation, then the set A quotient set is a partition, that it has all properties, and you can prove it. And also, the inverse theorem also holds that for any partition, we can construct equivalence relation on the set such that equivalence classes of that relation are exactly the elements of partition. And this is called a partition theorem. So that duality between partition and equivalence relations. And of course, it's nicely proved. So I never give a statement without the proof. So it's nicely proved. And this is called the partition theorem. And then you have, again, we covered equivalence relations. So you have a nice questions about binary relations, properties of binary relations, equivalence relation. For example, is it a transitive relation? Is there any equivalence relation on the set with 3 equivalence classes? Let's A be non-empty set such that there are exactly 25 partitions. Is it possible to define 20 equivalence relations of A? And of course, I give you nice answers to those questions. So, for example, let A be such that there are 25 partitions. It is possible to define 2 equivalence relations on A, because we can always define by theorem which brings equivalence relation and partition together, says that if you have equivalence relation, you can define as many as there are equivalence classes. So you can define up to 25 equivalence, up to 25 as many as partition of equivalence classes in the set A. And also you have some long questions. So for example, here's a function, and find equivalence classes of that relation. It means you have function from n to n given by nice formula, and the relations is that the values of that functions are the same. Of course, it's equivalence relation because it's defined by equality, and find the equivalence classes. And here's the solution. Again, what would be the equivalence class by 0? By definition, that f of 0 is equal f1. So it means fn, when you look at the definition of classes, fn equal, okay, so that would be n. 0 is less equals 6 when you look here. So 0 is here. So that would be the set of n, that n is less equal than 6. And also would be the same, and f, for example, of 7 would be greater. So you have only 2 equivalence classes, because you can see for any number less equal 6 would be here, and greater than 6 would be this equivalence class. Now, you have special types of relations. The other special important type of relation are the order relations. The order relations are relations which are reflexive, antisymmetric, and transitive, and there's a definition. And we say also that relations, the total order, or just order, if for any two elements are comparable, so you have also the fourth condition. And the order relation is historically called partial order, and the total order is called linear order. And so just for you to know that there are two different names for those two types of relations. And you have, of course, that is a natural order in the sets of numbers, and we use that as often as a symbol for any order relation, and we talk about graphs and so on, posets, special elements. So I don't want to spend too much time at that moment, but if at certain moment within the course we need that information, we will go back and use properties, and you use all this information. So now I want to spend a little bit of time on finite and infinite sets, because that is really important. So we say, that was Cantor who invented that notion. We have two sets, and we say that they are equinumerous. So equinumerous is generalization of saying have the same number of elements. That if there's a function, you can map one onto B. And now once we have it, you can think about this equinumerous relation. When you take a set and you have the set of all subset, that would be the equivalence relations in the set of all subset of X. So, and you can think equivalence class of any set would be all sets which are equinumerous. So it means for the finite sets, that would be all sets which have the same number of elements. For infinite sets, you need, first of all, you cannot say that there's no set of all sets. So when you have any set, you cannot, that relation is not, the set, it's not always defined in a similar way as we did for the set of all subset of a given set. So we don't use the notion of number of elements, we use the notion of cardinality. So we say that they are equipotent, or they have the same cardinality if you can map that one set one onto the other, and that is the notion of, we say that the cardinality, we have different notations for cardinality, and we can write A, B cardinality, or cardinality A equal cardinality B, or write A definition for all this notation is that there is F which maps 1 onto B. So they are the same in a sense of general sense of number of elements. And we use that notation for the cardinality. Say that two sets have the same cardinality. So it means we say that set A has the same cardinality as the set B if there is a function such that F maps 1 onto B. So you can just map. So now, what does it mean that set has n element? You say the cardinality is n if you can map numbers from 0 to n minus 1, because you have n. And we say that A has n elements. Now, the question, the next notion is, what does it mean that set is finite or infinite? You say it's finite when you can map elements into numbers from 0 to n minus 1. Infinite if it's not finite. The other sets, if you cannot map, like this, is infinite. And what does it mean how you can show that sets are infinite? To show that you cannot map is not a very easy way of proving. We have Dedekind theorem, which says that characterizes the infinite sets, that A is infinite if and only if there is a proper subset which you can put the whole set into the subset. It means you can map 1 onto A, 1 onto B. So it means you can map B is proper subset of A. You say that A is infinite. It means you can map the whole set into its proper subset B. And we'll have Pigeonhole principle, which says that you cannot do it for finite sets. So, for example, you can show that set of natural numbers is infinite because you can have a map Fn equal to n maps n 1 onto the into 2n. It means even numbers. Set of real numbers is infinite because 2 to the power x, you can see nice, 2 to the power x maps real numbers into R plus, a nice subset of real numbers. So you have two infinite sets immediately. And again, the question is, are those two infinities the same? You have a set of real numbers, and you have the set of natural numbers. They are both, we just proved, they are both infinite. Are those infinities the same? So the next thing we prove that they are not the same. The infinity of natural numbers is a special one, and we say that set is countably infinite if you can count it by natural numbers. So it means it has the same cardinality as natural numbers. And because they are very special, countably infinite is infinite because n is infinite, and countably because you can enumerate all the elements. So cardinality of natural numbers have a special name. And cardinality of natural numbers is called aleph 0 or aleph null. So aleph is first letter of Hebrew alphabet. And so we have a set of cardinality aleph 0. And we have that set is countably infinite if and only if elements can be put into 1-1 sequence by definition. And we say that, and in fact, if you have 1-1 sequence, you can, if you have a normal sequence which is not 1-1, you can always enumerate it in the way you throw elements that is just a sequence. And now we say that set is countable if it's finite, because it's countable. You have a function from 0 to n-1, or countably infinite. So it means the set is countable, or it's finite, or has cardinality aleph 0. Countably infinite has the same cardinality of natural numbers. Now we have so now we have countable sets. What is uncountable set? You cannot count it, so it means set uncountable if it's not countable. So now we have a new category of sets. It means that it's uncountable is infinite, and cardinality is not aleph 0. It means cardinality is not the same as natural numbers. So it means uncountable, cardinality of n, you can put all elements into sequence if it's equal. So it's uncountable that you cannot put elements into sequence. So now let's look at countable sets. Union of two countable infinite, union of two countably infinite sets is countably infinite. Countably infinite, you can put in sequence. You have 1-1 sequence. You can put union is listed like this. Is the union can be listed first from this, first from this. In case of disjoint, you have 1-1. In the case of not disjoint, you can prune that element, and you have you can enumerate all elements of the union. For you have two countably infinite sets N and B. What about the Cartesian product? How to list the Cartesian product? Cartesian product, you have the same Cartesian product, would be first of this and all. So you can see, okay, I count like this, but I cannot go to the next one. So is it a infinitely countable sets? And the question is, you can nice colors, that if you, this is infinite table, but if you look, if you have this, and now you do the diagonal, you see? And now you do the next diagonal. You do the next diagonal. So now if you look at that, infinite table on both sides, you can put them like this. You can string them by the diagonal, you see? And then you can, and in this way, you can put them on using those color diagonal. From here, you go there. This is finite, you go to the next. This is finite, you do the next. This is finite. You can list all elements of Cartesian product in one like this. And this is nicely by mathematical induction. That would be first zero diagonal, first, this is third diagonal, fourth diagonal. You can defined by mathematical induction, which would map the natural numbers into the whole all elements of the Cartesian product. And this is called union and product theorem. Now, the next thing is that the set of real numbers is uncountable. And we are going to prove it a little bit. That was your first homework in the book, but we are going to prove it in a few minutes. And I want to prove that set of real numbers uncountable. We prove the real numbers of interval 0, 1 is uncountable. And then we can map that, of course, this is 0, 1 is a subset of R. So if this is uncountable, R cannot be uncountable. So you have uncountability of set. So that we really will prove that the numbers of, it is an old Cantor proof that the real numbers of 0, 1 is uncountable. Now, real numbers, so you have now countable, infinitely countable, and uncountable. So real numbers are special uncountable sets, and they have a name. So the cardinality of real numbers is called continuum C. So, and we say that set has a cardinality continuum if it has the same cardinality of real numbers. So this is it's called a special cardinal number. So we already have a cardinal number aleph 0, null. This is cardinality of natural numbers, and you have C, cardinality of real numbers, natural and real numbers R. And we have certain sets of uncountable, it's uncountable set of cardinality C. So for example, positive real numbers R plus our cardinality of x equal 2 to the power x. I just erased this graph, it's still here, you see. 2x maps whole real numbers 1, 1 onto R plus, it means R minus R less equal 0. Plus it means without 0. Now, set of all subsets of natural numbers is uncountable. And we prove it soon in part 5. Now, moreover, so this is, we only show that it's uncountable, that you have the set of all subset of natural numbers, you cannot put them into sequence. But we have stronger theorem that the cardinality of the set of all set of natural numbers is C. So there are as many as real numbers. And this is not trivial. And as I say, it's out of scope of our possibilities at that moment. Let's put it like that. Now, the next, so we have like different, you know that you have aleph 0, you have C, this is infinitely countable, this is uncountable, and we know that at Cantor prove extremely important theorem that for any set Cantor, for any set A, cardinality of A is less than cardinality of the set of all subsets. So, for example, if you take natural numbers, So by Cantor theorem, this is the set of all subset of natural numbers. But then you can take set of all subset of this set, and so on. Of course, that would be also set of all subset of this set. So you can build the different cardinalities, the sequences of different cardinalities. And what you know also, that this is Aleph 0. Now, you know also that we proved that this is continuum, so you have, but that is 2 to the power. So it's another cardinality. And this is infinitely countable. This is uncountable. And here, all those numbers, cardinal, all those sets are uncountable. So you can see that you have a countable set, uncountable, and uncountable, and uncountable. So you have the notion of uncountable is, I rewrote it with p to the power n. The notion of all those sets are uncountable. So the notion of countable and uncountable, you have all those sets, only this one has the same cardinality as real numbers. And now you have, you can see, you can use those, at least, you have 2 cardinal numbers, you can use them and have like arithmetic of cardinal numbers. For example, Aleph 0 plus C is C, because this is a set of, and plus is the union. So union of infinitely countable sets, and the set of the same cardinality of real numbers has the same cardinality as the same set of real numbers, and you can define that as a plus of union, and so union of 2 sets is addition of 2 cardinal numbers. And also, so there's a lot of this is called arithmetic of cardinal numbers. This is important, that already I said that the set of all subset of cardinality, the set of all subset of natural numbers is uncountable set of cardinality C, and it has the same cardinality, the set of real numbers, and we write this as operation of those 2 numbers as 2 to the power Aleph 0 is C. But they are C, as many as real numbers, all functions that map n into n. So, and all functions that maps n into n are all possible sequences out of n. So in particular, you have that the set of all possible sequences that can form up infinitely countable sets, which is Aleph 0 to power Aleph 0, is continuum, and set of all real function of one variable have the same cardinality as the set of all subsets of real numbers. So that are simple properties, how you deal with those different types of infinity and how they relate and what they mean. And of course, we have some simple questions, which I will leave you to study, to help you to understand all this vocabulary. For example, set is uncountable if and only if I is a subset of real numbers. Set is countable if n is a subset of n. Is it true or false? 2 to the power n, set of all subsets of n, is countable. this set is infinite. This set is infinitely countable. Union of infinite set and finite set is infinitely countable sets. And of course, there are answers to study. For example, if set A is countable, if and only if has n as a subset of n, which is not true, because it's true only in one direction. Countable is finite or infinitely countable. So countable is finite. So if A is finite, that is not true. So that was a question about the notion countable. That is true if you put here infinitely countable. Also not. Okay, question is, A is infinitely countable if and only if it has n as a subset. A infinitely countable if and only if has n as a subset. Of course, in this direction is true, because infinitely countable cardinality of A equal n. So in particular, it's also not true, because you can have a set which does not have n of because the fact that A has as many elements that n doesn't mean that n is a subset of it. And there's, yeah, so there's more little questions with answers. Now, fundamental proof techniques, of course, they are, it means they are not fundamental proof techniques in mathematics. These are three fundamental proof techniques which are used in this particular subject and in this particular course. So, of course, we use mathematical induction, we use pigeonhole principle, and we use diagonalization principle. So, mathematical induction, example, for example, counting function, you have two finite sets, non-empty sets. The set of all functions which map A into B is the cardinality of B to the cardinality of n. So you can write it a little bit simpler form. It means if you have set finite of cardinality n, B of cardinality m, then there are m to the power n of functions f that map A into B. So you count, you have A and you have B, and you have to count, this has n elements, and this is m, and you want to count all the function. There is m to the power n of possible functions. Very useful theorem, and we will be using it often. And here's a nice proof. So, and then there is a pigeonhole principle. Pigeonhole principle, as everybody knows, right? If you have a set A, which is two finite sets, and the cardinality of A is greater than cardinality B, and they are finite, so it means that you have some finite elements and you have less elements here. So if you want to map you cannot map if it's more elements. This is 1, 1 onto. You cannot have 1, 1 function because you need to have some more than one pigeon in one hole. So this is your holes and they are your pigeons. So it means if you have two non-empty finite sets, there's no 1, 1 function from A to B, and in particular onto B. So we cannot, and there's a beautiful proof. There are two proofs. And this one proof uses the inverse image of B. That's why we're talking about the images and inverse images under the function. And the other proof uses really the image. So there are two proofs how you prove it by mathematical inductions. It's a nice, it's a very nice application of mathematical induction. So this is Pigeonhole principle as intuition, and the real statement of Pigeonhole principle is that if you have two finite sets, that A is cardinality greater than B, there's no one function A to B. And of course, we have to, and a nice inductive proof that it really holds. And also, the application is amazing. So, for example, one of important notions is for binary relation is the path in the binary relation. So the path is, if you have set A, the path A is a finite sequence, A1, AN, that they are related. AI, AA plus 1 is in R, and the length of the path is N, and then you talk, the length is N, and you get the cycle and so on. So that is the definition of a path we will be using. And the path theorem is that RB binary relation, you have two elements. If there is a path from A to B in R, then there is a path of the length at most cardinality of A, right? So the path you cannot, there is a path of length at most of how many elements are in A. Looks pretty obvious, but you need to have a proper proof. And how you prove it, suppose that we have a shortest path that from A1 to AN. It means, suppose that there is the path of the smallest length. We have n elements and you go. And suppose that that shortest path is n is greater than cardinality of A. By Pigeonhole principle, there is an element that repeats in the path. So you have AI equal AJ for some I and j between 1 and n. So then this path is shorter path from, because AI is equal AJ, is a shorter path from A to B that contradicted the fact that that we choose the shortest path. Diagonalization principle is, I will show you that you use that principle. It says really that if you have binary relation and you imagine that you have all these pairs, and you take the set of elements of A that the pair AA, you see, does not belongs to R. So if you take the set that RA, set of B, such that B, such AB is in R, that set is distinct from all that diagonal of that relation. So always such set is distinct from the diagonal. And of course, that was Cantor who invented and proved the diagonalization principle. And we use that diagonalization principle to prove that set to the set of all subset of natural numbers is uncountable, and we prove that interval 0, 1 is uncountable. And I will show you quickly that that second one, which is a little bit simpler. So let's prove the set of real numbers of 0, 1 is uncountable. And we do it by contradiction method. Contradiction method, if you say that something is not true and you carry your proof and you get a contradiction, it means that that contradiction proves that it was impossible for what you wanted to prove to be not true, so it must be true. So assume that 0, 1 is infinitely countable. So it means we can put all elements of the interval 0, 1 into 1, 1 function. So let's say that this are all elements, d1, d0, d1, dn, are all elements of real numbers in the interval 0, 1. Now, we get the contradiction showing that one can always construct an element in the interval 0, 1 such that is different from all elements already, which we assume they were all elements of 0, 1. So the contradiction shows that it's impossible to be infinitely countable. And how we do? We use binary, for example, binary representation of real numbers in interval 0, 1. So we write, these are all our elements in interval 0, 1, because we assume that they form a sequence. And these are binary representation. And we write it for 0 is 0, 0, 1, 2, 3, 4. Infinite, finite, it depends on the numbers. And you can see at d1 would be, you enumerate 1, and this is again the binary representation of d1, and what you have. And all those elements are from the set 0, 1, because it's binary representation. And now, you see, we look at this diagonal, and we take, so you look at this diagonal, and we change it. We change each element of the diagonal. For example, if b and n would be 0, if it was 1, you change. If this was 1, we change to 0. If this was 0, we change to 1. So that element, b and n, is not equal to all of them. And we form the number from those b and n's. And you know by diagonalization principle that that d is different than all these d's, because you can see what you form the number, you change all this. So if you change this is different than D0, you change this to B, is different than this, it changed to B is different this. So we prove that is. And you can do the same for decimal representation, and the Cantor, it's called Cantor theorem, because Cantor theorem was, that was invented proved by Cantor for the first time. And he used decimal representation, so that the proof is exactly the same, but now those elements are numbers from 0 to 9. And then you do, and then you, of course, you flip it in different way. For example, if it's 1, you can put 2. If it's not 1, you can put 1, or you can put 5, you can put 6, whatever you want. You make sure that you flip it. Okay, so now I think, okay, the closure is a very important notion. And we will use it at certain moment. And usually what I do, I bring the whole closure, the definition, later, because it's connected with the path. The whole notion of this reflexive transitive closure is this, that if you have a relation, so R star for any relation is the set of all elements of A, because R is a subset of A, that there is a path from A to B. So this R star represents the pairs which are the paths from A to B in R. And that is a very beautiful notation and beautiful notions which we will be used over and over. And also you have a very nice algorithm how to compute reflexive transitive closure of any binary relation over the finite set, right? So you have this, and then for each I tuple, do B1, Bn is a path, you add I, you add Bi, sorry, I have to fix. And also, and then you have a faster algorithm to do the same. And we will, and we'll use that notion of R for given relation R star is reflexive transitive closure of R, and really it represents a path between, and then we talk about the closure, reflexivity, whatever other closure properties, and then we have, we can prove, we have different definitions of the path, so you can prove that they're equivalent. That definition, you have different definitions of closure, and they are the same, but basically that is important, that R star is the set of A, B, always for any, is that there is a path from A and B in R. And we will use that, this path would be a computation in our automata. And of course, we show that you can define in different ways, and we do it. All right, so now we are part 7, the last one. So it's alphabet and languages. So data are encoded in computer's memory as strings of bits or other symbols appropriate for manipulation. The mathematical study of the theory of computation begins with understanding of mathematics of manipulation of strings of symbols. So we are going now to talk about symbols and strings of symbols, and introduce two notions, alphabet and languages. So alphabet, any finite set. Elements are called symbols of the alphabet, and that's why we say alphabet is any finite set of symbols. And we have notation. We use the, and I will put here, we use sigma to denote alphabet. So we can say that any, and also to call it alphabet, sigma is finite set. And of course, in particular, finite set, it can be also empty set. So sigma empty set is also a finite set. So alphabet can be empty. If we say let sigma be an alphabet, remember that it can be also empty. So if we want to talk about non-empty alphabet, you write sigma non-empty, so it's non-empty alphabet. And say you have symbols. For example, I can write, this is a beautiful alphabet. Three symbols. So this is alphabet. You can write n 10 to the power 10. That's a big alphabet. And elements are natural numbers. So that is called, if you have 0, 1, is called binary alphabet. And of course, we are not using any symbols if we want to talk about alphabets, so we will have certain way of denoting the symbols of alphabet. And because alphabet is a finite set, we will usually write that alphabet is A1, A2, AN, n greater equals 0. N equals 0, it means n equals 0, sigma is empty set. And we write also sigma in sigma, capital sigma and small sigma, as a general form of an element. And if I write that sigma is A, B, C, you have A is in sigma and so on. But if we don't want to specify which elements are, we say let sigma be in sigma. So that is. And also, we know that the alphabet is a finite set, so we can have all elements put into the sequence. So let's say we put all elements of alphabet into a sequence, finite sequence, you have a sigma. Now, finite words, so this is alphabet. Words over alphabet sigma are finite sequences, which we call strings. That's a nice over sigma. And finite sequences over empty included. And we denote, as I already said, E as an empty sequence. And we denote elements of for example, if sigma is 2 elements, so the sequences would be, this is a sequence, this is a sequence. But really, formally, the sequence is a function, 3-element sequence is a function from 1 to 3 into sigma, f1 equal 1, so that would be the first element of the sequence, f2 equal 2, second element of the sequence, and so on. So we don't use that formal definition all the time. We write sequences like this. And now, when you have alphabet, we denote sigma star. This is notation set of all finite sequences over sigma. And they are called words. So we write word in sigma star, and we denote word in sigma star. And we denote words by x, y, z, w1, w2, x1, x2, etc. in sigma star. So these are words over sigma. Words, let's write word over sigma. And of course, set of all finite sequences includes the empty sequence. So in particular, E is an empty sequence, is empty words, empty word. And of course, for any alphabet, sigma star is non-empty because E is always in sigma star. You can always sigma is the set of all words over any alphabet, because in particular, if you have alphabet is empty set, sigma star would have E, which is non-empty. And now you have simple questions. Reminder, counting function. So, for example, if you have k elements in sigma, how many there are possible words of the length less equal n over sigma star. So what is a word? You see, what is a word if you have of the length n? It is a function of 0 n minus 1 word of length n would be a function which maps into the sigma. And here the sigma was a1, ak. So we'll have k to the power 0. K is the number. So if you count, this set has n elements. You see, this set A has n element. This set B has k element. So if you have the number, so the number of words of length n would be k to the power n, counting the function b to the power a. So if you want to have length less equal 1, here would be the length 0, length 1, length n. So you have the counting, you sum all of them. These are the words, that many words of length 0, which is legs 1, legs n, so that you have the formula how many words. And now the general question is, given a non-empty alphabet, how many are the words of sigma star? So there is countably infinite many by sigma, because we prove that for any non-empty finite set, the A star is Aleph 0. There's countably many finite sequences over n. And we already proved that. And now you have sigma star, and we defined a language. The language is any language over sigma L is any subset of sigma star. So languages are the set of words, finite or infinite, any subset. And for any alphabet, the language is always countable. It can be finite or infinite. And for any alphabet, there are uncountably many languages. So the language is a subset of sigma star, so the language is infinitely countably. But if you take how many languages over sigma non-empty is, what does it mean? As many as subsets of sigma star, right? So as many as subsets of sigma star. And we know that this is, here you have sigma star has Aleph 0 is as many as real numbers. So you have precisely continuum as many as real numbers of languages over any non-empty language. So you can see you have little alphabet, one element alphabet. You have infinitely countably languages over one element alphabet. Infinitely countably words over one element alphabet, and you have uncountably many languages over one element alphabet. It means exactly as many as real numbers of languages over one element alphabet. And of course, alphabet is countable because it's finite or countably infinite. And for any alphabet, I just said there are exactly as many languages as real numbers. Its proof is here. In particular, if you have one element alphabet, there is alpha 0. It means infinitely countably languages over one element alphabet. Of course not, because there is as many as subsets of sigma star, and sigma star is Aleph 0, so 2 to the power Aleph 0 is C, and of course Aleph 0 is less than C. And now we use this definition to define the length of the word. So the word is always a function. So n is the length of the word. So we have, and now you can, because the word is a function, you can define the position. You have a word, you can define a position of an element in the word. So for example, A is in the first position, N is in the second position, I is in the third position, T is in the fourth, and A is in the fourth. So, and then you can say that one occurs in the position here. You have a string of 0, 1. So it means you have a function if you have so that word is a function between 1, 2, 2, 8, because this is 8. That should be 3. That 1, 2, 3, 4, 5, 6, 7, 8. And now you can see that 1 occurs in position 2 and so on. So you can formalize what you see with your spy with little eye. And now we have operations on words. The first operation is called concatenation. And concatenation of two words, you have two words, means that you write one word after the other, and this is the symbols of concatenation. If we want to stress that we deal with concatenation, we use the symbol. If we don't, we just write x, y followed by x. And here's a proper definition of concatenation. If W is a concatenation of x and y, if the length of W is the union of the lengths, in W, 8th position is x to the length of x, and now the follow is yj, where j is to the length of y. And now we have that properties of concatenation, that you concatenate the empty word. On any side is the word, and is associative. So, and we prove it by mathematical induction. And then you can see, we can define the substring, prefix, suffix, and so on by the definition. And now we can define the power of the word. It means you define that power 0 is e, and I plus 1 is I concatenate with w. So, for example, when you have w square would be 1w, so ww. And then reversal, that is important. We define the reversal. Given a word, we define the reversal. Short definition is that reversal of E is E, and if you have a word, it's inductive definition, and A is element of alphabet reversal, you get A and reversal of U. And now you prove, for example, that for any two words x, y, reversal is x reversal, y reversal. And do it by mathematical induction. Nice, pretty exercise on mathematical induction. And so, given an alphabet, I repeat that language is any subset. So any language over sigma is finite or infinitely countable. And also languages can be finite languages. You can enumerate them, but often are defined by property, like sets, right? Sets can be defined. Language is the set of all words which fulfill certain property. For example, let's have a language that W has even numbers of 0. Or let's say language, another language, W has AB, because they are all strings of AB, that AB is a substring. Now you have another language that all strings 0, 1, then the length is less equal 2. That's an easy one. This is a property, and here length is less equal 2. So it's length 0, length 1, length 1, length 2, length 2, length 2, length 2. So you have a language given by property. Also, languages are sets. So you have all operation of sets on languages, right? You can have union of languages, intersection, difference of languages, complement, difference of languages, like difference of sets. Complement of the language is sigma minus language. You can have Cartesian product of, so everything which you do with set, you have with languages. But, of course, we have a special operations. And special operation is concatenation. So given two languages, you concatenate two languages is the set of words which are concatenations such that X is in the first language and Y is in the second. So we can have a new operation of languages. First is a concatenation of languages. So L1 concatenated L2 is the set of X. I want to say the same as was on the slide. W in sigma star, that W equal X concatenated with Y, where X in L1 and Y in L2. And here you don't write the concatenation. That means concatenate words. And also, of course, when you look at this, I said sigma star, languages can have different. So you can always say that language 1 is a subset of sigma 1 star, and language 2 is a subset of sigma 2 star. So concatenation, you can always say that this is a subset of sigma 1, sigma 2, or bigger set. And so you can always assume that the languages are under the same alphabet. So that's why you write sigma here. So for example, let's say the language are A, B such that W is less equal 1, and this is less equal 2, and I want to find the concatenation, so the domain would be the alphabet A, B, 0, 1. Now, if you have a finite set, it's easy, right? You have one language and the other, and now you can list them, and then you want to concatenate, so you can write the concatenation is E and concatenate with this, B, A, and concatenate with all Y in the second, and now B concatenated with Y, Y is L2. So general formula, you can write that L1 concatenated is E concatenated with L2, which is this part, union A concatenated with L2 and B, so you can write it in more general. And now you can, for example, you have two languages, and let's say L1, W has even number of zeros, and L2, W is V 0 XX, when X is in sigma star. And when you take L1, L2, so what you get odd number of zeros, and L2 and 1, W would start with 0, and then you have all elements of sigma star. And you have different, and of course concatenation is not, concatenation is not commutative. And now when you have some languages, it's different ways how you describe the concatenation, by property or by certain formulas. Now, important first theorem, that concatenation is distributive over union of languages. So it means this is union of languages, you concatenate with L, you distribute, and on both sides, on this side is distribute. And you prove it by mathematical induction. Very simple. And here is proof for n equal, base case equal to, very simple proof. Next operation, so on languages you have concatenation of languages, and the next operation on languages is called Kleene Star. You will see, which is L star. Kleene, mathematical mathematician, logician, American logician from University of Madison, already pass away, but he got the name. Small operation, but very, very important in theory of computation. So that's why he got the name. So L star is the set of all strings obtained by concatenating 0 or more strings from L. Simple thing, but has so much, is so important. So formally you write, what does it mean? L star is W1, Wk, k greater equals 0 of, because this is L, so W1, Wk is in L. Or you can write Wk greater than 0, We is in L, I equals, so this is a different way. Or also you can write generalized union is the union k greater equals 0, W1, Wk of those, you see, because of length 1, and W1, Wk in L. And of course, it's the same, we write here concatenation of words without the concatenation. And you have different property. E is L star for all L. L star is non-empty for all L. That is important property. Empty star, empty, nice, sigma equal empty. So you start with empty alphabet, and empty star is non-empty, because if you have L star is empty star equal E, which is non-empty set. We already played with it. And you can have that L star is sigma star for some L, for example, L equals sigma, and for some it's not, because if you take, for example, L is 0, 0, 1, 1, and sigma over 0, 1, so you have 0, 1 is in L star, and 0, 1 isn't in L star, and you don't can, if you have L star of this, you don't have 0, 1, and this is in sigma star. And of course, that property is a trivial example of the language, such that L star is equal sigma star. Can you have non-trivial example? And here's non-trivial example. If you have a sigma 0, 1, and you take all w's such that w has an equal number of 0 and 1, so for example, the words looks like that, and we prove that L star is, for that, you see, L is not sigma, is sigma star. Very nice. So let's prove that L star is 0, 1 star is a sigma star. So L is a subset of 0, 1, and 0, 1 star star is the same. So, and you have property, if L1 is included L2, then L1 star, the star, you can star on both sides. So when you have L star would be 0, 1 star star is 0, 1, so L star is a sigma star. And of course, we know now to show that sigma star is in L star, but 0, 1 star includes that set of words which have an equal number of 0, 1. Because 0 is in L, because 0 is regarded as the string, has an equal number of appearances of 0, 1. The number of appearances of 1 is 0, the number of appearances of 0 is 1, so 1 is in L for the same reason. So we prove that 0, 1 is in L, and we use the property that you can star on both sides. And now you defined another operation of languages. So we define L star and we define L plus. It is like L star, but k is greater equal 1. So L plus is the set of words that K star, K could be 0. And you have different properties. L plus is L concatenated with L star. And if E belongs to L plus, if and only if E belongs to L, and we prove different properties. Now, this is important, that we can express a finite language by finite means to, for example, listing all the elements. If finite language, you can list is a finite means. Languages are often infinite, and so a natural question arises if a finite representation is possible, and when it is possible when a language is infinite. Because you want to represent those languages in computers, and you can only represent finite things. So the representation of languages by finite specifications is a certain issue of the theory of computation. Of course, we have to define first formally what we mean representation by finite specification, or more precisely by finite representation. So, for example, look at this language. I have language like this. It has A, B, A, star. So it is represented by a finite number of symbols. A, you can count them. But by definition of Kleene Star, A star is infinite set, E, A. So the same, so here you have this union. B is just a B. Here you have concatenation with A star. So you can write it as E, A, B, A, B, A is infinite. So here is finite representation of that infinite language. So we want now to see how you can represent infinite sets by finite specification. And the Kleene Star is very important. So you can say that this expression is built of finite number of symbols, right? That's 1, 2, 3, 4, 5, 6. And it describes this expression describes the infinite set. Also, instead of writing this, we can write this expression in simplified forms. Instead of writing those set and Kleene Star, you can just write A star instead of set, which has A as an only element, and the same from this Wiglis you can list. So that would be my finite representation of that set, which represents infinite set L. And that is the idea of finite representation. And this expression we called a finite representation of the language. So what is a finite representation? We use symbols. So for the finite representation, we use a symbol. So we have a finite number of special symbols. You see, and Kleene Star is there. So we have a symbols. You need parentheses. You need a symbol of Kleene Star. You need the union, and you need the empty. That represents the empty set, you see? And you have this, which represents E. And, of course, plus C, any element of sigma. Sigma in sigma, sigma is alphabet. So an alphabet is finite set, so all the sigmas are finite, and you have finite elements, and then you have extra elements. And this one, we use those expressions to describe the language. So here's a language. This is an example from the book. It's the only example the book gives. So that's why I'm talking about the lecture notes, which has a little bit more than the book. So let's look at the language. W has 2 or 3 occurrences of 1, the first and the second of which is not consecutive. Nice property. The language, this, can be expressed in terms of as a set, as a 0 star, 1 concatenated, etc. The finite representation, you skipped the set symbols, and that would be a finite representation of that language. So and now our problem will be, of course, you have to see that really that or that language has that property. So the question is, can we finitely represent of languages over the alphabet? And of course, we want different languages must have different representation, and finite representation are finite strings over the finite set, so they are countably many, infinitely countably many of possible finite representation. So of course, not all languages can be finitely represented, because we know that there are uncountably exactly as many as real numbers of possible languages. So we can only represent certain languages, right? And we prove that all strings are Aleph 0, so we have continuum of languages, so we have that we cannot represent finitely all languages. So not all languages can be finitely represented, and languages which are finitely represented are called regular languages. So there are uncountably many, and exactly as many as real numbers of languages that cannot be finitely represented. We can finitely represent only a small countable portion of languages, and we study here 2 classes of languages which are finitely represented: regular and context-free. So now we are going to define a regular language. So we say that R is a regular expression, you see, expression which is finite string over all our expressions we want, right? And is the smallest set that empty is regular expression, sigma is regular expression, and we have that empty. It means empty is regular, and all sigma in sigma are regular. And now you have a concatenation, union, and Kleene Star. It's close under concatenation. We skip the concatenation, union, and Kleene Star. So this is called regular expression. And of course, the set is countably infinite. And you have some examples, right? You have 0, 1, and you code. Now, when you look at those expressions, we defined that we put concatenation in parentheses and union in parentheses. So because we need, but there's a lot of, some of those parentheses we can skip. For example, without, we can keep essential parentheses, because you know that, for example, the union is associative, so you can, you see, instead of writing those parentheses, you can write this, and then if you have this, you can write that. So you can skip those you can keep only essential parentheses, so let's simplify a little bit. So we use regular expressions as representation of languages, and languages represented by regular expressions are called regular languages. So the idea of representation, for example, this is a regular expression in shorthand notation. And now when you look, what does it mean? This represents that language. So you see I write here. This is a regular expression. And now the language that represents a set. This represents also a set. And here's a concatenation, which we don't write, right? This represents a set. Language is a set. And union. And here you have 0, 1 string. So this is language. And if you want to see what this means, it is E1, 1, 1, 1, 1, infinite, concatenated with 0, 0, 0, 0, 0, concatenated with 1 again, E, or E, I forgot to put E here, and union, and that would be Kleene Star. You have E, and now you have 0, 1, and then you have 0, 1, 0, 1, etc. So you see, this is infinite language. This is infinite language written as a language, and here is your irregular expression. And now you have a function which, this is the function which establish empty, that is regular expression is empty, sigma, sigma, so it means 1 becomes a set, right? And then concatenation here is concatenation of languages, union, symbol of union here is union of languages, and Kleene Star is Kleene Star. And we say that definition, the language is regular if and only if it's represented by regular expression. And of course, this function is regular into baba. So instead of writing that L is represented by alpha, you just write L equal alpha. So here I could write that L equals that expression, right? It means this is a shorthand. Instead, writing that this is our representation, which is really that whole thing. And if you want to see how it looks like this. So in shorthand, instead of writing this L, you say that L is represented by that expression. So it's a useful shorthand notation instead of writing each time this function L. So for example, if you have this is regular expression, now when you look at regular expression, you can say, oh, I don't need those parentheses. So I can shorten it. But I need those because this is union star, so this is a shorthand. And now you can ask, what is the language represented by that expression? So let's say now I have my expression, regular expression is A, B, star, A. And what would be the language represented by that? Language would be our function of this alpha. So what it would be, the function L would be A becomes A, B becomes B. This is now the union of two languages and concatenate it with A. And now you can write, so L would be, this is one element set, union one element set. So this is A, B, concatenated with A. But language, this is just sigma. Language was over sigma star concatenated with A. So these are all elements of sigma star with ends with A. And here I wrote you, if you have this function, how it works out. But really, you can go from here and write this and this immediately. And this is not a regular. This is sigma star concatenated. So that would be the set of all W that ends with A. And there are a lot of examples. And here is this how to describe. And here I nicely describe the property that is really that expression has that property W does not contain the substring 1, 1, 1. So class RL of regular languages over alphabet sigma contains all L such that L is represented by alpha. So RL is a class of regular languages, all languages over sigma star, that they are represented by certain regular expression. And of course, we have how many? There is alpha 0 regular languages because there are alpha 0 of regular expressions. So you have countably many regular languages. And we have that the class of regular languages is the closure of the set of languages, one-element languages, with respect of union, concatenation, and Kleene Star. Because of that, one expression becomes one element. So really, you have any element of sigma becomes the sigma, the language sigma star, and then you have union, Kleene Star, and concatenation, and you need parentheses just to see how you work. So we know that they are continuum as many as real numbers languages that are not regular. So we have a natural question, how to prove that a given language is regular. Easy. You find a regular expression. If you find a regular expression, you know that is. How it's not regular, it's not easy. So we have a theorem which is called pumping lemma. We prove pumping lemma by pigeonhole principle. That's why we're talking about pigeonhole principles and proving pigeonhole principle theorem to be able to prove the pumping lemma. So we'll have a theorem called pumping lemma, which provides a criterion of proving that given language is not regular. For example, this language is regular because it's given by that regular expression. We will prove using pumping lemma that the language 0n, this is star. Star means any number of zeros. 1 means any followed but any number of ones. That language is 0n is n number of zeros followed by n number of 1, where n is not regular. So it means that that language is the same number of zeros follow the same number of ones follow the same number of zeros. It's not regular. It looks like regular expression, but it isn't. That is regular expression. So general problem is, given a language L over sigma and a word, how to recognize whether the word is in the language or not. And that is our next subject, which are the automata, which are language recognition devices. And we will be building language recognition devices called automata, which would, and not for all languages, for which languages we can have language recognition devices, which we could decide if the word is in the language or is not the language. So that would be our next subject, would be finite state automata. Thank you very much.